Different shape conductors. Suppose say I have here a tapered rod. Let me just introduce to this thing. So I'll connect this across a cell. So let the radius of this end be A, the radius of this end, let it be B. We have to find out the expression for current through it. So let L be the length along the axis. Now we have to get expression for the current. Go back to thermal conductivity. Here, along with this, we'll discuss the drift speed, electric field, all other quantities. So whenever you enter into the inside the conductor, don't just bother resistance. All the parameters of Ohm's law, relaxation time. Of course, relaxation time depends on material here. Let's not bother. The drift speed, electric field, current density, the resistance of different parts, different sections, power dissipated per unit length, all the parameters you have to compare at various points. So how to find out the resistance of this? So I'll assume a small element. So let this be the small element. So radius of this, let it be R. Thickness of this, let it be dx. So let it be at a distance x, I'll assume. Then what is the resistance of this small element? Let it be dr. So how to define? Now, you can ask questions. Why you assumed thin disk? Okay, let's come back to the current here. So current I will flow now. So here the current density will be directed in this direction. Then how you should assume always the elemental structure should be such that the current, it should be the area of cross section of that should be directed normal to current density, because everywhere the current will be flowing along this direction. So how the current density will be along x-axis. So perpendicular to j bar, the elemental structure should be assumed. This is one basic rule. So what is the resistance of this small element? dr should be equal to rho dx into area. Area of this is pi r square. We can't integrate directly, you know. So I should bring the terms. So you look at this triangle b minus a, b minus a, this will be, and this will be r minus a. This is x, this is theta. We'll agree this triangle. So tan theta from this, I can write it as b minus a by l equal to r minus a by x. So what is r is equal to? B minus a l x plus a. I'll differentiate this. dr equal to b minus l into dx. Let me replace the dx term in the above equations. So dr equal to rho, dx will be L by b minus a into dr by this is pi r square. So rho L pi b minus a r to power of minus 2 dr. So the limit will be from a to b. The radius at one end is a, at other end it is b. So we'll get rho L pi b minus a minus 1 by. So this will be rho L So therefore, what is the effective resistance will be rho L by AB. So this is a resistance of this particular given conductor. Let's come for the quantities. What will happen to current density at 0.192? We will just compare here. Current density is at 0.192. One by one, we'll compare it here. At 1, current density, area of cross section at 1, it is less compared to 2, no? A1 less than A2. And what is the expression for current density? Current by area, same current will flow, because the reason 1 and 2 are in series, the structures will be in series. So therefore, J1 greater than J2. What about the disk speed? J equal to current density is directly proportional to disk speed, no? So the disk speed at 1 will be greater than that at 2. What about electric field? J equal to E by rho. So E1 should be less than E2. What about the resistance of elements? Resistance of elements, where area of rho L by A. Rho L by A, where area of course less, they're more resistance. So R1 greater than R2. Provided similar elements I'm picking up. Let me give one rough diagram. These are the two identical elements we picked up. So sorry, of same thickness we have picked up, then we are comparing them. This element 1, this element 2. What about the power dissipated in those elements? The when where current is same through them, where resistance is more power. So P1 greater than P2.
How did you get the relationship for E, sir?
J equal to E by rho, no? This should be greater. Because same resistivity, no? The material will have uniform resistivity. Can you say anything about potential differences? Potential difference. So what is the expression for potential difference?
V1 greater than V2.
E1 greater than E2. So same dx in that. So delta V1 greater than delta V2. So every numerical, irrespective of shape, I took here truncated cone or tapered rod. What is this? Resistance of a tapered rod. What we calculated is resistance of a tapered rod or truncated cone. So in every, so don't forget this, because this part is what the conceptual, which will help you a lot in numericals, especially more than one options. Along with this mathematical things, they'll include these things. So if you work out some 2-3 different shapes, no, you'll get overall picture. Okay, this is what I should do. Rather than fighting with concept, no, make a practice of this one. Different shaped conductors, not just finding out the resistance, you should compare all the other parameters that are related to Ohm's law. What are other parameters? Like a disk speed, current density, electric field intensity, then whatever the resistance of that elements, potential difference across the elements, power dissipated. Okay, fine. So I'm making it a rule. Just practice few, it'll be in better position. Because you see in EDO, in few problems is asking these things. What will happen to? So students will think something conceptual they're asking. No, it's everything through mathematics we should conclude here, not something like we have to make a guess. Got the idea, no? So anything if they ask you something, so assume the basic equations you have, apply them properly. Okay, similarly, we'll go for spherical conductor. So this resistance of this be A, inner area B. So let this be iron, and let this be air. I'll connect a cell between inner and outer surfaces. So I want the potential, or so like the resistance. Then we'll compare all other parameters. Here, if you want really, so you can assume like this. This is a cell. So where the cell is connected from the inner one to the outer part. Okay, we have to assume a. Now, what is the resistance of this material? So let rho be the resistivity of this. Form resistivity, let it be. So this is a thick shell, thick conducting shell. So what I do is like I'll assume here first a thin shell. Not symmetric. Yeah, fine. Okay, let's go for a thick shell. Let me assume. Okay, let this be a shell. Okay, let the radius of this shell be small r. Thickness of this, let it be dr. Now, very first question, sir, why you assumed shell? How actually current will flow here? What is the direction of current? What is the direction of current? Will be radially outward, no? This will be how the current density, everywhere the current density will be like this. So then how we should assume elemental structure such a way that the current density should be directed normal to surface area. I'm giving the direction of J bar. Hmm? So now first the resistance of that thin shell, dr should be equal to rho dx. What is the surface area of that? 4 pi r square. Sorry, dr it is. So this will be rho by 4 pi r to power of minus 2 dr. The resistance will be from where all the material is present from A to B, the radius from A to B. Rho 4 pi minus 1 by B plus 1 by 4 pi AB. So there's a resistance of the thick shell. Okay, I want the expression for current density. So what is the total current I? This I should be equal to applied EMF E by R, no? E 4 pi AB by rho B minus A, or this will become 4 pi EAB by rho B minus A. This is the expression for current. I want current density at a distance R. So what is the formula I should pick up? J should be equal to what should be the formula? So J should be equal to I by pi r square. What is I? I the constant, no? You can see everything is pi r square. So as you move away, tell me what happened to current density here. Will decrease. So this will become 4 EAB rho B minus A R square. All terms are constant. Applied EMF, radius inner, and so J is proportional to 1 by R square. So you take 2 points in a the thick density, no? Yes, it'll be different here. The same diagram, I'll just indicate all the other terms. So this is the point 1. So we are comparing current density at 1 and 2. So where current density will be more, R1 will be less than R2. So J1 greater than J2. What about E1? Greater than E2. What about the disk speed? What about the disk speed? That the speed is directly proportional to current density, no? So the speed of the particles will be more at 1 than it. All other terms, like what we had, no? The similar way what happened, we can analyze here. Thick iron shell. Can we calculate potential difference between any 2 points? Yes, we know electric field vector. So we can determine potential between any 2 points inside the conductor. So dV equal to E into dr formula. We can calculate potential difference between any 2 points. Any of the things can be asked rather than just ending up with only this answer, no? So you just do focus on other parameters which are missing in book. So definitely in exams, they'll try to pick up the other things which the books didn't analyze. These things. So how to calculate potential difference? So dV is equal to minus of E into dr. Substitute value of E as a function of R, then integrate. This will be from R1 to R2. Okay, got this. So we can determine potential difference between any 2 points inside the conductor, no? Where when battery is connected. Okay, tomorrow I'll continue from here. Tomorrow we'll discuss few more problems related to all these applications. Okay, fine. Thank you all of you. Take care. Counseling from 6 to Satish Sharma sir, if you take chemistry, no? Take 6 to 7, 7 to 8, I'll be there. Or 6 to 7, 7 to 8, depending upon which batch you'll engage, no? The other batch I'll be engaging. Okay, fine. Okay, thank you all of you. See you tomorrow. Bye. Take care.